Good afternoon. So I hope that you had enough time to rest a little bit and recover your energy. So we continue. Today is the last lesson we talked about abstract algebra. So we want to talk about normal subgroups and factor groups. So the first thing I want to define, what do we mean by a normal subgroup? Okay. So if you remember, if we have a group G, and then if I have a subgroup of that group G, yes, we could talk about left coset and right coset for any element of the group. And if I choose one element, any arbitrary element in my group, I can construct the left coset containing A, which was denoted in this form. AH, if you remember, was the set defined to be A times H, where H belongs to H. That is called the left coset containing left coset of the subgroup H containing A. And we learned that this is not necessarily a subgroup. It's a subset, but not necessarily a group. And I ask you to prove that this only becomes a subgroup if and only if A belongs to H. If A does not belong to H, this then turns out not to be a subgroup. Okay? And this is called left coset. Similarly, we can also have the right coset containing A, which was very clear, means H times A. This time H belongs to H. Okay, but in general, we didn't talk. So this was what we learned about left and right cosets, but we didn't talk about what we want. There is sometimes these two become equal for any choice of A. If that happens, then I would say that I am facing a normal subgroup. Okay, so that's the definition of normal subgroup. So when we say G is a group, and then H is a subgroup, we say that H is called a normal subgroup. And we denote it by this. We put a triangle like this. And some books, they put also equality there. So whenever you see this symbol, it means that H is a normal subgroup of G. H is called a normal subgroup if for every choice of A in my group, the left coset containing that element is equal to the right coset. Okay? So if this happens, I would say that my H is a subgroup, as a normal subgroup. Okay? So this is an easy exercise. I want you to prove it yourself. This is equivalent to saying that for all A in G, A, H, A inverse is equal to H. Okay? And then hopefully you now can guess what is the definition of this. Yes, what is the definition of that if you want to define it? It is the set consisting of all elements of this type in which H belongs. Okay? So this you can do it yourself. So there is no difference. Some books they define the normal subgroup in that way. Some books they define it in this way. This is the way that your book has chosen. Okay? So this is something you can immediately do yourself. Any questions so far? Okay. So now this is the first example. It's extremely simple. Show that I want you to remember this as well. Okay, not just as an example. Show that every subgroup of an abelian group is normal. Yes? I hope that you can see why. So this is the example one. What is it telling me? It means that G, an abelian group, and then H is an arbitrary subgroup. What is the claim? The claim is that H is definitely a normal subgroup. So it's good to remember this as well. So any subgroup of an abelian group is automatically normal as well. Okay? Yes?
Is any normal subgroup always abelian, regardless of the
No.
Okay.
So let us see why this is true. Why this is true? If I want to show that this is a normal subgroup, I have to check this definition that if it is correct or not. So if I want to solve this, I would say that let A belongs to G. We prove that what AH is equal to HA. Okay, so this is the definition if I want to prove it. And then of course, you know this is equivalent to proving what? So let me write it here. In order to prove this, I have to prove two things, yes? One, I have to prove that AH is a subset of HA. And number two, I have to show the other way around, yes? HA is a subset of H. So this is something you already know. Okay, so let me just prove one, because they are very similar. So what should I do? I want to prove that a set is a subset of the other set. The standard method is I pick an element here and prove that that element is also in the right-hand side. Okay, so I would say let X belongs to AH. Okay, we prove what? We prove that X belongs to HA as well. Okay, but tell me, what should I do? So, if X belongs to AH, what is the conclusion? X belongs to AH means that X takes the form of the elements in this coset. So this means that it is guaranteed the existence of some H in H, such that what happens, X becomes equal to AH. Yes? But what you know, H is from H, but H is a subgroup of G, so this means automatically little h is in G as well. And from the beginning, I picked A from G. Yes? So A and H are both in G, and G is abelian. So this means there is no difference between AH and HA. So this means that, and this is equal to HA, so since G is abelian. Yes? But if I ask you, where do you think this belongs to? This belongs to capital H times A. Yes? Which belongs to capital A. So that's it. So I chose an element in A times H, and I realized that the same element is also in H times A. So we proved this one. You can prove this one yourself. That's very simple. Understandable? It's very simple. Okay, and then let us see what I have here. So this is a checkpoint. It's very similar to this one. You remember we had something called the center of a group. We learned that if you have done the checkpoint before, you already learned that the center of a group is a subgroup of the group, but we want to go more today. You're supposed to do it yourself and prove that the center is also a normal subgroup. So we can say more. Okay. Any questions? And here I am not saying G is abelian. G could be any group. Yes. But the center of it is a normal subgroup. Okay. So this theorem is usually good, because I want to go through the proof of it, because you learn a little bit about normal subgroups. Okay, so here I told you before, so here if you remember, what is the difference between this and the definition? So if I show you in the board, I didn't prove it, but I told you that this is equivalent to this one. Somehow is understandable for you, so we are just multiplying by A inverse. So what you see here is exactly this definition. So some books choose this one, some books choose this one for definition. But in this theorem, we want to prove inclusion from left to right is enough. You don't need to check the other way around, because the other way around is automatically done. Is that clear? So what I want to show, so theorem 1, what I want to show is that if G is a group and if H is a subgroup for the time being, and then so let me write it like this. H is a normal subgroup if and only if for every x in G, x, H, x inverse is a subset of H. Yes? So what does it mean? Of course, if you want to prove a group is normal, you can prove this, be my guest. No one will criticize, yes? But this is a little bit easier because you don't need to prove equality, you just need to prove inclusion from left to right. Okay, so do you understand the difference now between this and the definition? So in the definition, I have to prove equality, but this theorem tells you that you don't need to prove equality. If you can manage to prove inclusion from this left to right, it is guaranteed that your group is normal. Is it clear? That's what we want to prove. Okay, but because this is if and only if, I want to give you a little bit of hint and some proofs, okay? Or it's a sketch of the proof. This one is simple. I agree, so we have the assumption that each H is normal. I want to prove this. That's very simple, do you agree? Because if H is normal, and X belongs to G, what can I conclude? I can conclude this because of definition, which hopefully you can show is equivalent to this one. So I can say that H inverse is a subset of H. Is equal to H. But if it is equal, so it is also a subset. How weird. Yes? Because this was very clear. But now I go the other way around. So I know for every element that I pick from my group, this holds. I want to show that H is a normal subgroup. So I would say that, so this is my assumption now. But now I want to prove that H is normal. So what can I say? I would say let A belongs to G. We prove that AH is equal to HA under that assumption. Okay, and you know this is equivalent to saying that, again, AH is a subset and HA is a subset of this one as well. Yes, so number one and number two. So let us do number one, you can do number two yourself. Are you following or not? Is that clear? Okay. So now I want to prove this one. Again, the same technique. Yes, I would say that let X belongs to AH. We prove that X belongs to H. Okay, so but when you say that X belongs to AH, this exactly means there exists an H in H, such that what happens, X is equal to A. Do you agree? Okay, but how can I proceed? Remember, what is my goal? My goal is to show that this X that I have chosen and takes this form now will also be in HA. But what do I have in my hand? I have this assumption in my hand. I know that no matter what X you choose from G, including the one that I chose here, including this A, yes? This is working for every one X in G, including the one I picked from the beginning myself, okay? This holds. So in other words, if you replace X with A, you will have A inverse is a subset of H, and it is guaranteed. Why? Because this was true for any choice of X in G, including A in G. Is that right? Okay. Now, how can I use this idea? So I will multiply this by A inverse. That is not very hard to come up with, yes? Because I want to have the structure of AHA inverse, which is exactly this type of structure. So this motivates me to multiply from the right by A inverse. And then what happens, this becomes XA inverse is equal to AHA inverse. Okay, but you tell me now, if I ask you where this is, one simple answer is it is in G, of course, but that's not very constructive, yes? So if I want to limit it, where do you think this belongs to? No, why? I mean, in the beginning. This is not guaranteed to be in H. By this assumption, it will be in H. I agree with you. But if I ask you where is it coming from, what do you say? Can you give me a set? Not G. G is correct. But forget about G. Another set, which is guaranteed that contains this one. What is the structure? A, little h coming from H, and A inverse. So if I write this belongs to A, capital H, A inverse, do you agree with me? This element is of the type of the elements within this set. So definitely this belongs to this one. But now what is my assumption? I know this is true for every choice of X in G, including that A. So if I say that this itself is a subset of H, do you agree with me? Yes or no? Hopefully yes, yes? And then what I can conclude, XA inverse is equal to this expression. This expression is definitely in this set, and this set by this assumption is a subset of H. So this means that XA inverse belongs to H as well. Do you agree? So what does this mean? This means that there exists, I have used letter H and H prime. There is no guarantee that this H is the same H there, so I put it H prime, such that XA inverse is H prime. Okay, and then what do? I multiply by A from the right. So what I can get that X is equal to H prime A, and I know where H is, where H prime is. H prime is in H. So can you conclude something about this? Where do you think X belongs to now? X is an element from this set multiplied by A, but A is on the right side. So where is it belonging to? Where does it belong to? HA. And that was my goal. Yes? We proved that AH is equal to HA. So do you remember, let X belongs to HA. We proved that X belongs to, and this is done. And of course, you have to continue with 2 yourself. But it's very similar. So it's up to you. It sometimes saves a little bit of time, you know. Instead of proving equality, prove only inclusion, but this one should be included the other one. Any questions? Understandable? Okay. So now let us go to the next. This is a good example. So let us do it together. So let me describe it on the board here. You can see it yourself. So do you remember what was this group? General linear group. When we write this, what do I mean by that? Do you remember? It's a very famous group. It is the group of all 2x2 matrices whose elements are coming from R, but one condition, because that is not a group yet. If the determinant is 0, we do not have inverse. So we have to impose that condition to guarantee groupness, big group, yes? So this means the set consists, the group of all 2x2 matrices with real entries with non-zero determinant. Okay? And then we learned, hopefully before, this is one of the famous groups, so it's good to have it in mind. Before, after exam you can finish it, but before that it's better to remember it a little. Okay, and there is a famous subgroup for it, and that was called a special linear group. So in the very beginning of the course, hopefully one of the self-check points is to prove that this is indeed a subgroup. What is that? Do you remember? What's the difference between SL? So GL means determinant is not 0, but does not specify any value for the determinant. SL is the ones that determinants are equal to 1. Okay? So anyway, if you have forgotten, no worries. Here we put all 2 by 2 matrices, determinants are non-zero. Here we put all 2 by 2 matrices, determinants are equal to 1. Of course, automatically it is also non-zero, but that's a special case, and that's why a special linear group. Okay? So hopefully you already know this is supposed to be a subgroup. So I am taking that for granted. And now I want to prove more. I want to prove that this is indeed a normal subgroup. Okay? So the question is SL2R, we want to prove that this is a normal subgroup of this one. So again, I already assume that you already know this. It's a subgroup. We want to prove it's a normal subgroup. Let us use this theorem. Okay? So how you start the theorem? The solution. If I want to show that this H, if I want to show that H is normal in G, I have to show this is valid for any choice of element X from the original group. So what should I prove here? I would say let X be in GL 2 and R. Okay? We prove that. Okay, can you help me? What do you think I will write in this empty space? We prove that what? I want to use that theorem. Did you eat too much? Yes, don't do that. Yes. That's why this is my lunch now. Yes. Yes, please.
Where we X in GL, it implies that X.
No, I want to exactly copy, more or less copy and paste the theorem for this case.
Yeah, so can't you say that for every matrix or
for every X, which means a matrix.
GL,
Yes. What should I write? We prove that what?
X,
X, capital X.
SL,
Exactly. SL, 2 and R. X inverse is
it's a subgroup.
a subset.
Subset, sorry.
Of course, it becomes automatic. Yes, there is no guarantee that this is still a subgroup. Yes. So this should be SL2R. This is what we want to prove. Yes. We prove this. But in order to prove this one, what should I do? If I ask you what is this relation is between two sets. So in other words, I want to prove that this set is a subset of that one. Okay, so again, the same technique. So there's no confusion. If you follow the rules, it's very easy. So this is a set, and that's another set. I want to prove that this set is a subset of that one. So what should I do? I would say let. Okay, but by the way, when I say this one, what is the meaning of this? What is the character of this X? What is this X? By seeing that, you understand that X is a matrix, 2 by 2. Entries are coming from R, but one more thing. What is that? I just described it for you.
Non-zero determinant.
Non-zero determinant. So by this assumption, you automatically guarantee that this determinant is not zero. Okay? Because that's the definition of GL. Okay, now I would say let M belongs to that set. We prove that. Can you complete my sentence, please? We prove that what? I want to prove that inclusion. I'm just waking you up. These questions are extremely simple. So what should I do? We prove that. Hurry.
Determinant.
No. Why we prove that?
M is a subset.
M belongs to. Yes? Is that right? Because I want to prove this inclusion. I pick an arbitrary element from the left-hand side, and my goal is to show this in the in the right-hand side. Okay. But let us try to understand that. If I want to prove that M belongs to SL2 and R, I have to show that this is a matrix 2 by 2 with real entries, and more importantly, the determinant of M is equal to 1. Is that right? So that's my goal. So, of course, M is a matrix. Yes, because when you say it belongs to here, so let me write it here in this one. So when you say this one, this means there exists a matrix in SL to an R such that, okay, help me, M is equal to what? You see, this is a set. These are fixed elements, okay? So when you say M belongs to this set, it means you could find a matrix here so that M is equal to, what should I write? X, A, X inverse. Is that right? That's the meaning of my assumption. Okay, if this is the case, what was X? X was originally a matrix. A is originally a matrix. So it is clear that this combination is finally a matrix. But it is not guaranteed yet that this is inside this. What I have to show, I have to show one more thing. We prove that. Help me. We prove that what?
Determinant equals 1.
Exactly. So determinant of M is equal to 1. And if the determinant is 1, it's already a 2 by 2 matrix with real entries. If I can guarantee that the determinant is 1, then it is definitely in that SL. Okay, so let us do that. So how can I prove that? M is equal to XA, X inverse, and then the determinant of M should also be equal to the determinant of X, A, X inverse. But hopefully you remember that much from linear algebra. What I can write here, I can write determinant of X multiplied by determinant, because all of them are square matrices, 2 by 2, and the determinant of X inverse. But I can continue, so this becomes determinant of X, determinant of A. But do you remember that theorem from linear algebra? What can I write for the determinant of the inverse of a matrix?
1 divided by
1 divided by that. Is it guaranteed that I can do that? Yes, because this determinant is not 0. So that's the reason we really need that. So because that determinant is not 0, I can write it as determinant of X. Okay? So this one and that one are cancelled, so I get determinant of A. But what is determinant of A?
1.
Why? Because A comes from this set itself. So it means that determinant of A is equal to 1. So this means that this is equal to 1, and end of story. So it's a very, very simple, exercise, but it helps you to understand and digest what is the meaning and how to use the theorem. So I more or less need nothing. Just write the very standard way of writing things. Any questions? No? Okay, so now this is a little bit tricky. I want you to learn this one. Okay, let me describe it here for you. Okay, you can read it, of course, yourself from the slides, but I prefer to describe it here for you. So it is what was theorem 2. Any questions, by the way? Are you following? Okay, good. So theorem 2 tells me what? Let us say that if I have a group G, okay, and then I have a normal subgroup. So that's extremely important. So let me write it with a different color here. Yes, and then you will see somehow why. So H is not just a group, is a normal subgroup of G. Okay? So now what I want you to do is to take all left cosets of this and put them in a set. Okay? So what I mean you open a set, find all left cosets, put them in this set. What does it mean? It means that all left cosets, okay? And for the time being, I know that I have chosen a different notation in my notes, but if you don't mind, for the time being, let me call it M. Okay, so our claim is that we want to define a binary operation on this new set. Okay, so what you have a group, you have a normal subgroup of that, and then you can find all left cosets. If you remember, we did one of these type of exercises before. So you find all left cosets and put them in a bag, in a new set, and call it M. And my goal is to define a sensible, a definable, well-defined binary operation on M. And how I define it in this way. I would say that pick 2 binary operation means what? You have to assign exactly one element from M to every ordered pair from M. That's the meaning of having a binary operation. So we define it in a natural way. So I would say that AH star, where is it coming? It's a left coset of H, it is in M. I want to define this binary operation multiplied by BH. Where is this? BH is a left coset, so it is also in M. I want to define it semicolons equal to AB times H. Okay, so if I ask you where this is coming from, I hope you agree with me, it is coming from capital M because it's a left coset of H. Where this is coming from, the same set M. Where this is coming from, the same set M, because that's also a left coset of H. Okay, so in other words, I am trying to sell you this idea that this is a binary operation on M. It is not that wrong, so it is not something that you immediately say, no, it is wrong, because I am respecting my own rules. I am picking 2 elements from M, and I am giving you another element from M. That's the meaning of having a binary operation. But binary operation is a function, so I have to make sure that's a function. Why this matters here? Do you remember this function I told you before? So something like that. Do you remember something like this? Do you remember if I say this is the set of Q rational numbers, if I say that this is a function defined in this way, do you remember this was ill-defined? Yes, why is that? Because we can have different names for the inputs and the outputs are different. But for a function, the equal inputs should go to the equal outputs. Okay? So this is also happening here. And that was the reason I brought this example back then, so that to prepare you for here. Why is that? Because it is possible, if you remember the previous lessons, I'm not going to repeat them, but it is possible that A is not equal to alpha, but AH is equal to alpha H. This can happen when we have cosets. Okay? So that will be the same trouble we had back then. So if I want to prove this theorem, I have to guarantee that this is well defined. So we want to prove that. Let me write proof. To prove that this is a binary operation, I have to show that this is well defined. We show that a star is well defined. Okay, but because this is very famous in abstract algebra, you should be able to tell me what does it mean. If I want to say that this operation is well defined, what should I show you? When do you become convinced that what I told you is correct? I want to show that this binary operation is well defined. It means that I want to show that this is indeed a function. What is the meaning of a function? It means that if the inputs are guaranteed to be equal, the outputs should also be equal. That's the meaning of well-definedness when it comes to a function. So now I want to say that this star is a well-defined binary operation. So help me. What should I prove for you? It means that if the inputs are the same, but the inputs of a binary operation is an ordered pair. Okay? So in other words, this is, by the way, it's very important. This is not something, if you want to take something out from algebra course, it means you should be able to immediately tell me what does it mean to be well defined. Okay? So this means that if AH is equal to, alpha H, what does it mean? It means AH and alpha H are different names for the same entity. Okay? And if, can you complete it? If B Say something.
H,
BH is equal to
beta H.
beta H. I want to guarantee that what happens.
A comma B equals alpha comma beta.
Yeah, but don't jump in me very. So it means that I want to prove that AH star BH also becomes equal to what? Alpha H star beta H. Do you agree? So this is what we want to prove. We want to prove that if the inputs for a star, it means that the ordered pair of this and that is equal to the ordered pair composed of these two are the same. So the outputs are also the same. So that's the meaning of well-definedness. Yes or no? Okay. But before doing that, we need something. So let me recap a little bit because probably you have forgotten. So recap. So let me completely write with a different color. So recap, if you remember, we defined, if I give you a group, and I give you a set, a subset, okay? Do you remember we defined a very famous equivalence relation using the subgroup on G? So there was a famous equivalence relation on the original group using the subgroup. Do you remember what was that? At least you remember something like this. Once upon a time, there was something like this, yes? And that's good, that's enough. So what we want to do, that relation, I would write it here. Then, this relation, the relation, tilde, defined on G by, for all A and B in G, A is related to B if and only if A inverse B belongs to H. That was the famous relation, yes? Then the relation defined on G by this is an equivalence relation. We had this in this previous lesson. And one more thing. Moreover, do you remember what we derived for cosets? Sorry, for the equivalence classes? Moreover, for every A in G, the equivalence class of A was equal to the left coset. Okay? So, if you've forgotten, this was very, very simple. So, but this is what you need to remember now, okay? So this is an equivalence relation. So therefore, what we can say now, we can say that so how should I write it? It will be good. Okay, so AH is equal to alpha H. Can you complete it for me? This happens if and only if AH is the equivalence class of A, alpha H is the equivalence class of alpha. Okay? But when, do you remember, this is very important to remember, when two equivalence classes are equal, we had this before in general, before even reaching to this part, when we were talking about equivalence relations. Two equivalence classes are the same. So do you remember the typical example was being a classmate? So when the class of you and the class of you are the same, you are in the same class. So it means you are related. So you don't need to remember that much. This is a very standard example. So this means this happens if and only if what? If and only if A is related to alpha. Yes? But what is the meaning of this? This is the meaning of A is related to alpha means, so let me write it the other way around. It doesn't matter, of course, because you know that this is symmetric, so it doesn't matter in which way I write it. So let me write alpha here and A there. And then according to this relation, this happens if A inverse, oh no, that was good. Sorry. So I don't want to confuse. So let me keep the same. So alpha inverse A belongs to H. Yes? So remember, so you can forget about everything in the middle, and you realize when two left cosets are the same. They are the same if and only if inverse of one of them multiplied by the other one belongs to the subset, so subgroup. Is that right? So what I want you to remember is this fact. AH is equal to alpha H under this condition. Alpha inverse A belongs to H. This is what I want you to, of course we did very good recap now, but now you don't memorize. You know where this is coming from. Of course you can prove it using set theory as well, but this is a better way to see it, why this is correct. Is that right? Okay, so now the recap is finished, I come back here. Okay, my goal is to prove this equality, but I have two assumptions in my hand. One of them is this one of them is this one. So I know these two are correct. I want to guarantee that this equality is also correct. Yes? So, but if you don't mind, let me write this in a little bit better, easier way. So this is equivalent to, so let me write it in this way. This is equivalent to ABH, by definition, is equal to alpha beta H. Do you agree? And this itself is equivalent to what? According to the yellow line. Can you help me? If I want to prove the equality of these two left cosets, if I want to prove the equality of any two left cosets, what I need to prove? I need to prove the inverse of this alpha multiplied by H itself belongs to my subgroup. So now I want to prove that these two left cosets are equal. So what should I prove? Can you tell me? I should prove what? Yes? The alpha beta inverse multiplied by AB belongs to H. And by the socks and shoes theorem, this is also equivalent to saying beta inverse. Yes? Alpha inverse AB belongs to H. Do you agree with me? So, I will focus my energy to use these two pieces of information to prove this last line. Because this last line is equivalent to what I want to prove. Is that clear? Yes? Okay. Now, so let me draw this line and then the proof, the continuation, proof continues, yes? Okay, so let me manipulate a little bit because it is not very clear what to do. This is belonging relation. What I have, equality relations. So let me put them in the same footing, okay? So this means that I will start from here and manipulate my data a little bit. But help me, what is the conclusion? It is on the board, yes? It means alpha inverse A belongs to H. And one more piece of information. BH is beta H. What is the conclusion? Beta inverse B also belongs to H. So I know this. My question is this. If I can guarantee from those pieces of information, I can conclude this, I am done. Yes? But do you have any idea what to do? It's always tricky for me. So let us start from here. We have beta inverse, alpha inverse, AB is equal to. Do you have any idea what to do? So you see, this combination is nice because I know something about it. Yes? That is not unfortunately enough. So what should we do? So the trick is if I can remember because I don't want. So I would put beta inverse here. So yeah, just bear a little bit with me. And then I put beta here. Okay? But I cannot just put beta there unless I just get rid of it. And then how can I get rid of it? By putting beta inverse and B. Yes, now you are extremely happy, are you? Why? Because this is something I know something about. Yes? And this is also I know something about. And I'm also counting on you. What do you think I can do? What can I say about beta inverse and beta? Can you tell me? So this one is definitely in H. Do you agree? My claim is that this one is also in H. It is not obvious yet. What I know is the middle one is in H, but there is no guarantee yet why this collection is in H. Can you tell me why? And then you realize why this is important that I put in red. Okay, so can you tell me why that is in H?
There was something, it was like a sandwich theorem thing, I don't remember.
Yeah, it is here. No, it's not sandwich, it's up there. Exactly, yes? So if I have a normal subgroup, if the normal subgroup is sandwiched between an element and its inverse, that is a subset of the group, of the subgroup. Yes? Do you agree that this has the same combination here? This element belongs to H. One more thing. Do you agree that this belongs to beta inverse capital H beta? Because this is an element from H which is sandwiched between beta inverse and beta. So this is the whole combination is from this set. But this is now a normal subgroup which is sandwiched between one group element and its inverse. Okay? It doesn't matter if the inverse is on the right or on the left. X and X inverse are just one inverses of one another. So this H is sandwiched between a group element and its inverse. So what can I say? Because H is normal, what can I write? This is a subset of H. Why is that? So let me write, because H is a normal subgroup of G. Okay, so what happened? This was in H. This combination was in this, and because H is a normal subgroup, it is also in H. So this one is in H, this one is also in H, and H is a subgroup, so it is closed under multiplication. So this means that this is also definitely in H. And that's it. That's my question mark. Is that right? Okay. So then you see that was the reason that we have to have a normal subgroup, because if there is no, this is not normal subgroup, this is not guaranteed that this becomes in H at the end. Is that understandable? Okay, one more thing that we want to talk about now is that there is a notation for this. We don't call it M, so the notation is G divided by H. Okay? And then next theorem after the break, this set with this binary operation that I define will be a group in its own right. And that group is called the factor group or the quotient group. Is that right? So is the structure clear a little bit? Okay, but that's a good time to have a little bit of rest so that I can also clean the board. Thank you.